In this module, we're going to look at BGP routing and the attacks on BGP. We have talked about how the TCP/IP works and how some of the essential infrastructure like the DNS works. There's one more essential infrastructure that we're going to talk about, and that is BGP. And BGP is what glues network together. So we're going to look at how that works. And we're going to start with a high-level picture to show you how the internet connect together. The internet is consists of many networks, and they are called autonomous systems. So we're going to look at the autonomous systems and look at how they actually get connected together. We call the peering. Based on that understanding, we're going to look at the BGP protocol. To connect two networks, you need two types of connection. For two networks to be connected, they have to be physically connected. This is one the essential connection. Then the other essential connection is a software connection. So just physically connected, that is not enough. They have to allow each other and to forward information to the other side. And that is done through the BGP routing. And so we're going to talk about the BGP protocol. Based on understanding of the protocol, and we're going to explain one of the interesting things called IP Anycast. We have seen that in the DNS, some of the root server, for example, F root server, it is distributed into many different places across the globe, but just one single IP address. So how can multiple computers in different locations use the same IP address? And that is a very interesting. We're going to look at how that works based on the BGP. And we're going to talk about BGP attacks. When people launch an attack on the BGP, the consequence is going to be very severe. BGP is glued the network together. So if you can launch the attack on the BGP, you can bring down the entire internet. We're going to look at how the attack works, and we're going to look at some of the case studies. After that, we're going to talk about how we can secure BGP. Before we dive into BGP, I'm going to show you a very interesting observation. So I live in a place 15 miles away from my university, Syracuse University. It's only 50 miles. And so when I'm at home, I was trying to see how my packet get from my home to my office. So I used a trace route and to figure out the path of my packet. I was very surprised to find out that my traffic take a huge detour before reaching the university. So let's take a look at the traffic. So I'm doing the trace route to the university, and you can see the first few hops there just from my home, and eventually go to the Roadrunner. So that's the ISP that provides internet service to my home. And from there, it actually gets routed through several Roadrunner routers. If you look at the name, and you will be able to figure out where those routers is. From here, you can see this is Albany. Now the traffic actually went from Syracuse to Albany. And then from there, it actually went to the NYC, which is New York City, about 250 miles away from my home. And then from there, it's still be in the NYC. And then it connects to another internet service provider, Cogent. And if you look at the name, that's JFK, that's JFK Airport. So usually many routers, they use the airport code and for their name. From JFK, it went back to Albany and eventually came to Syracuse. And you can see it took a huge detour, and the round trip is about 500 miles, but my house is only about 50 miles away from the university. So how come? Why can't it just directly go to the Syracuse? So if you understand how the internet are connected, how the internet works, and you would easily understand this phenomena. And you can actually do the trace route from your own house. You can do the trace route from your own home and to see what is actually the actual path going from your home and to the place you work. And some of you probably going to find out huge surprise, maybe longer than 500 miles. Give it a try. To understand how the internet works, I'm going to understand the routing. So in this lecture, I'm going to actually provide a very high-level picture of how the routing works. The internet routing is quite complicated. So we're going to look at a high level first, and then we're going to zoom in to some of the more specific. As we have seen in the previous lectures, the routing depends on routing table. So when the packet arrives at the routers, and they're going to rely on the routers to tell them and where to go. Now routers relies on the routing table and to decide where to route the traffic. Now the question is, how is the content of the routing table be set? Who is going to set that? Let me just use an analogy to help you understand the whole process. Just imagine we are driving, and in the old days without the GPS, in order to go from one place to the other place, we usually depend on the maps. So we're going to have the map and we look at the actual route from A to B. So that's how we actually drive. So that we're going to rely on a map. Or sometimes we don't have a map and we're going to rely on the sign. So when we get to somewhere and driving on the highway and we see the signs, to this city go this direction, for that city go that direction. So we actually rely on either the map or the sign so we can get to the places. The internet is pretty much doing the same things. So we need a map. The signs are actually based on those maps. In the physical world, those roads, and once the road is there, it's going to be there for many years. Tomorrow is going to be there. Next year is going to be there. So your map is going to be very static. And the signs are also going to be quite static. Sometimes they close some road and they change the sign, they put a detour signs in there. And that happens. But internet is very, very dynamic. That road that was there yesterday could not be there tomorrow, even the next minutes. They could be done, and then you have to take a detour. And just imagine the signs that you put on the roadside. And that just means whenever your map changes, you're going to have to redraw the sign. So the internet is quite dynamic. The question is, how do we get this map? You still need a map. You still need to know how to get anywhere, but this map becomes very dynamic. They can change very often. So we cannot afford to statically set our routing engine. The signs that you see on the roadside, they are static set. But in the internet, you cannot afford to do that. But then how do we set up the signs? The routing tables, they are the signs. How do we set up them? Let's just take a look at big pictures. The internet, they consist of a lot of these networks, and they call it autonomous system. Some of the autonomous systems, they are the end user, like the universities and the companies. Some of the autonomous systems, they are the highways, and we call the transit. They are the national backbone, just like the national highway, interstate highway, and some of them, they are regional, and just like the state highway. So you have a lot of this network, and they are connected together. This autonomous system, and they are connected together, and that forms the internet. But physically connect together is not enough. Everybody needs to know the map. So how do they actually come up with the map? Those links that you see on the diagram, they can change very dynamically. So the map can change very dynamically. But how do they get the map? And so this is where the BGP comes in. Every autonomous system, they have this BGP speaker, and at the edge, okay? So they are at the edge. Whenever you connect with the next one, and you will have set up the BGP speaker. So these are the BGP speakers. And they're going to actually exchange information with one the other. For example, this one can say, I can reach this network. So I'm going to let everybody know through my BGP speaker. So I'm going to let you know that you can reach this one through me. And then everybody's just going to actually further disseminate. So eventually, every autonomous system and their BGP speaker, and they will know how to reach this final destination. And that is map information. So basically, everybody is going to actually keep announcing their information, the network that they can reach. And then they actually announce to the entire world and through their neighbors. They tell that to their neighbors through their BGP speaker, and their neighbors can actually further disseminate that information and through their neighbors. And gradually, the entire world knows in order to get that destination, and I can go to this network, that network, and eventually arriving at you. So everybody now got this picture, and that is the map. And that is the main purpose of the BGP protocol, is to disseminate this routing information to the entire world. So everybody in the world, everybody means the BGP speaker, every network, they do have a representative in the form of BGP speaker. They will collect the global information. They have the map. Now with that map in mind, now within their network, they can disseminate the information within their network, and that's where you can repaint the signs. So for example, this one, let's say this one is a national backbone. It's an interstate highway. So inside of this, there are a lot of these actually internal routers. So the information collected here at those BGP speakers is going to be disseminated into this internal network. And that's where this internal network router can be configured. Their representative knows the map, and they just need to send that information to the every routers. Internal router do not need to know the entire map. All they need to know is the sign. If they want to go to Seattle, go this direction. If they want to go to San Francisco, go this direction. They only need to know what their next step is. They don't need to know the global picture. And that's what the sign is. So basically the BGP speaker is going to collect the global information, the map, and then disseminate it into their internal routers, and then internal routers can repaint their signs if things are changed. That's how the internet works. It's through this BGP speaker which communicate with each other and to collect the global information and then disseminate the information into their own internal routers. And therefore, when the packet go from one autonomous system to another autonomous system, within that autonomous system, they still have to go through several hops, just like what you see in my previous traceroute traffic. In the Roadrunner, internally, it actually went through several hops. In the Cogent, it also went through several hops. And that is because the information collected by the BGP. This is the high-level picture, how things work. But the actual details is very sophisticated. So we're going to dive into some of that, but I won't actually cover every details. If your job is to configure the BGP routers, and you probably have to learn more, and here I'm trying to help you understand how the BGP works, not at a very high level, but with a decent amount of the low-level details. And so you could understand the attacks. That's what we're going to do in the rest of this module. In this lecture, we're going to talk about autonomous systems and the peerings. As we have talked about in the previous lecture, the internet consists of many autonomous systems. The autonomous system is not just one network. They could include many networks. They belong to one single entity. So a company, it doesn't matter how big or how small they are, they can become autonomous system. So their autonomous system could be a small network, or they could be a huge network like the national backbone. And they have cables from the coast to coast. They come with various size. And there are three types of the autonomous systems. The one type is called a stop. So they are just like a company. So if they have a company and they have a network, and their network connect to an internet service provider, they are receiving a packet from the ISP or sending the packet to the ISP. So in order to reach the internet, they have to go through the ISP. So this is called a stop. They have one single ISP. There's another type called a multi-homed. For this type of autonomous system, they connect to multiple autonomous systems, and this is called a multi-home. They can connect to the internet through two different autonomous systems. In case one link goes down and you still have another one. So this is called a multi-homed autonomous system. And the third type of autonomous system is called transit. The main purpose is to provide the transit service. So the packet comes from into there, and they're going to actually hold the packet and to some other places. Okay, that's called a transit. They can connect to many autonomous systems. The packet comes from here, and they will be routed and eventually routed out to those places. So they provide a transit. And this stop and multi-home, and they usually do not provide the transit. For example, here, now even though packet can flow from here to here, but if I'm not a transit, I'm not going to allow this to happen. I'm only going to use you and to send or get the packet, but I'm not going to actually provide a transit service to you. So because I am not a transit type. But for this autonomous system, that's their main business. And their main job is to provide a transit service. And that's also how they make money. And those are the internet service providers. Some of these transit, they're large and they across the globe. Some of them, they are small. They probably cover just one region, for example, the state and the transit service. Okay, so you're going to see variation in terms of size. And let's look at how those autonomous systems are connected. We have talked about it before. When they get connected, it's called pairing. If two autonomous systems and they want to pair, AS1 and AS9, they want to pair, and what they will do is, and they will have a physical connection so they can reach each other physically. And also they're going to set up the BGP speaker. This is the BGP. And they're going to set up BGP speaker, and they're going to be connecting to each other and through a TCP connection. And they're going to exchange information using this TCP connection. And that's called peering. They will run the BGP protocol. So I'm going to tell you the network that I can reach, and you're going to tell me the network that you can reach. So we're going to exchange information. And then if I select you as my next hop destination to a certain destination, and I will forward the packet and to you. Now pairing can happen either privately. So two of us, let's do a pairing. I want to exchange traffic with you, so let's do a pairing. So that's going to be a business side to decide who is going to pay who. Okay, usually the small guy pays larger guy. Okay, so we're going to do the pairing. That's private pairing. So we're going to actually find the data center. We're going to put our BGP speakers inside the data center, and then we're going to connect. And we're going to establish a TCP connection so we can exchange information. And some of the pairing, they happen in the larger facility. They call it internet exchange place. And a lot of these network service providers, and they have a presence. They are peering with one another. Okay, so that's called internet exchange point. Some of internet exchange point, they are huge. They connect the net from different countries, different continents, and together. For example, one of the facility in Manhattan, and they actually connect a lot of huge network service providers. So these are the public peering, and this is called IXP. Now once they have peered, and they will just disseminate information to each other. For example, here, I know how to reach this IP address, 128.230.0.0/16, and then I'm just going to actually, through the peering, I will tell you this BGP speaker is going to disseminate information to its own pairs internally. And then this one, all of this, and they're going to further disseminate the information regarding this network and to the outside world. As I mentioned, the peering can happen privately in a data center or publicly in an internet exchange point. Peering is basically done through a switch. Different network, and they're going to connect through this huge high throughput switches. So if you look at these examples, and this picture is one at Amsterdam Internet Exchange. And you can see this is huge, the switch, where BGP speaker, and they're going to connect to each other and they can exchange information. And this is the one that I was talking about in the Manhattan. This is Manhattan landing. You can see it connects a lot of network, a lot of actually huge internet too. And here you have Taiwan, you have Canada, and you have a lot of this international and backbone, and they come here and they peering with each other. And so they can exchange traffic. That's how the internet is connected, through this internet exchange point or through this peering. And this is a map that shows you the location of many of the internet exchange points. So you can see the autonomous system, they peer with each other in many of these different locations. It is very common that the same autonomous system, they peer with each other in multiple locations. So not only just in one single location, and they're going to peer in New York City, in Chicago, in London, in many, many different places. So you don't actually just exchange the data into one single location. You could exchange information in different locations, so you don't take a detour. So now if you go back to the traceroute example that you see, the Roadrunner that I've been using is my internet service provider connect with a Cogent, not at a Syracuse, but at New York City. And that's why the traffic that I put on the Roadrunner, they could not get into the Cogent. Cogent is the one that's going to eventually deliver my packet and to the Syracuse University, because Syracuse University is not on the Roadrunner, but it's on the Cogent. And the closest place where the Roadrunner and Cogent connect is in New York City. And that's why my traffic goes all the way to New York City and they take a detour, come back. If Cogent and the Roadrunner and do a private peering inside Syracuse, then my traffic will not take this detour. But Syracuse is not a large place, and many of the internet service providers, they will not and do the private peering in here. Syracuse doesn't have this large internet exchange point. So a lot of this peering is through the private peering. And the Cogent and the Roadrunner did not do the private peering and in Syracuse. And so that helps you understand your traffic pattern because of this connection point. They all have to go through this connection point so they can get from one autonomous system and to another autonomous system. How they decide where to connect, and that is because of the routing. So that's the BGP part that we're going to talk about. I will show you some of the case study. So Syracuse University, so the autonomous system number is 11872, and this is network, the address, so 128.230/16. It connects to 3 different autonomous systems. 174 is Cogent, and this one is the NISONet, and this one is the level 3. So the Syracuse University have 3 pairs. This Syracuse University is just the customer of this internet service provider, and this is multi-home because we connect to the multiple links. Some of these links, they are not primary link, they are backup. But we do have these 3 in case one goes down and we still have 2 links where we can reach the internet. And you can find out the neighbors of any autonomous system through this link, ripe.net, and provide a lot of actually useful information about the BGP. And this is NISONet, the autonomous system 3754, and this one is the New York State regional backbone, and it's mainly used for educational purpose. And so you can see it cables and runs from the Buffalo and to Rochester, Syracuse, and Albany, and then down to the New York City. And so Syracuse and connect to this autonomous system here because it's passed through Syracuse. Now, in order to connect to the other network, there's 2 points At Syracuse, NiceNet does not pair with many other networks. In order to go to another network, for example, go to the Internet 2, which is a national backbone, and we have to go either send our traffic to Buffalo, to the west side, or we can go to the south side to the New York City, and where it can get on the Internet 2. So that's actually how the NiceNet works. It's a state-level backbone. This one shows you a larger one. This is Cogent. This Cogent is a national or international backbone. It covers many, many different places. And you can see it has the presence at the Syracuse, and that's where my university and get connect to the Cogent. But it has many, many different places here in the US, in Europe. And if you look at these places, these are the internet exchange point where they can connect it to many of the other networks. So if you are in one of these places where there's no presence of Cogent here, Cogent may give you traffic to your state level backbone, and from there, and it may actually eventually reach you. So if I send the traffic from here, so my traffic will hop onto the Cogent network and get pulled all the way to here, and where it has to exit from the Cogent network and go to the state backbone and eventually reach the end customers. And so this few example, you can see the autonomous system of different size, from a small company or university and to this state backbone and to the national backbone or international backbone. Each of them is represented as one autonomous system. So by looking at the autonomous system, you won't be able to see their size. So you can see the size of autonomous system, and they vary a lot. In this lecture, we're going to look at how the BGP works. As we have talked about, that autonomous system and they pair with each other. When they pair, and they will set up their BGP speaker, and their BGP speaker is going to connect to each other through the TCP. And then they can use this TCP to exchange information. And this is called a BGP session. To keep this connection connected, and they will periodically send keep alive information to the other, so the other end will know that this connection is still there. If the other one does not receive the keep alive, and they're going to think that this connection is broken, and then these two autonomous systems cannot reach each other. Okay, so they're going to keep sending the keep alive. Now, the most important thing for them is to exchange information. Let's see here, I'm at the Syracuse University. I own this network. I need to let everybody know. Because right now, none of them know that they can reach this network. I want them to know that if they have a packet going to 128.30, I want them to send to here. But how do I let them know this? And I'm going to send them the information. That's called a BGP update. So I'm going to send this BGP update. This is called a prefix advertisement. I'm going to advertise my prefix. This is called a network prefix. I will tell them that I can reach this network 128.230.0.0/16 and through this 11872. Okay, so I'm going to send this information to here, and same thing, I'm going to send the same information and to them. And this way, and they know that they can reach 128.230 network through 11872. And this is called the AS path. So it contains autonomous system. And right now there's only one node on this AS path. But now the next autonomous system, they're going to further disseminate the information to the rest of the world. For example, all of them, after receiving this, and they're going to actually further disseminate, and they could receive multiple. For example, this one could be connected to here. So this one, 174, and it's going to see that to reach this one, I can go through here, It also knows then to reach this network, I could also go from here. So it's going to actually select one of them. So in this case, I'm going to select the one. So for example, I'm going to select this one because I can directly connect to this. So I am going to further announce it to the outside, the next one that I'm connecting to, autonomous system. So I'm going to announce to them, telling them that I can reach this 128.230.0.0/16 network through 11872. I'm going to add my own autonomous system number in front of that, on the left side of that. So that's called the AS path. And so what you do is you basically select among all the AS paths that you have received for each particular network prefix. And then you pick the best one that you like, and you forward to your other neighbors. And this way, if everybody is doing that, now gradually, now the entire world, as long as they are connected to the internet, and their BGP speaker is going to pick up this information, so they will know how they can reach the 128.230.0.0. And each of the autonomous systems, they may get different route, and really depend on the topology. And that's how the advertisement works. And it really just starting with the owner of that network prefix, and then further get disseminated to the entire world. We will talk about how this path is selected. Like in this case, this one will also advertisement to here. So it will say you can reach 128.230/016 11872 3754, and this will be sent to here. So this one actually get two, one directly from the owner and the other one from here. And this one is going to pick one and then further advertise to its own neighbor. And there are different criteria that we're going to talk about later on, how to pick the best path. When they send this AS path to their neighbor, this is called a BGP update message. Let's take a look at what the actual update message looks like. And as we said, this BGP, they use TCP. So you can see I'm using TCP. The BGP listen to port 179. So that's the standard the port number. Inside one TCP, you can have a multiple update message. So you can see this packet have a 4 update message. Now each one for one network prefix. I'm expanding one of them. You can see here, this is the update information. I'm telling you I can reach this network through this AS path. So the last one, this is the one that originate this network prefix. This is the owner of that IP prefix. And this is the one who is sending that to me. Because when they send this update to me, and they're going to actually append and their autonomous system numbers in front. So this way I know in order to reach this network, and I will go through this autonomous system, then go to this autonomous system, and eventually go to this autonomous system. And there's one more thing I need to know, which is the router information. So if I use you as my next hop, and you gotta tell me your router's IP address. So that is here the router. So if I decide to give my packet to you, I will just give it to these routers. Autonomous system itself is not enough. I need to know the concrete information about routers. And this is called the path attribute. And these are the essential attributes, the AS path and the next hop. Inside the same update, you can also have a withdrawal message. So I'm going to talk more about that later on. When the BGP message arrives at one autonomous system, this autonomous system is going to actually know multiple paths to the same location. And they're going to maintain all of this. Okay, they're going to have this table maintaining all the AS paths they collected from their neighbors. So for example, here, let's see, each of them, they have announced they can reach the destination P. They're going to say, I can reach this location P through AS1, and I can reach this P and through there's some more autonomous system number here through the 3. And same thing here, I can reach this from this and then through the P. This is my AS path. This autonomous system is going to maintain all of these paths from each of the autonomous system. So you're going to see a tables inside this BGP speaker. It's going to say to reach P, I can get from 1, 3, and 4. This is the list of the AS paths. Now I need to announce this to the outside, to all my neighbors, including to them. They are all my neighbors. So this autonomous system need to pick one. This autonomous system does not announce all the AS paths to its neighbor. So it has to pick the one for their routing. So they can say, if I route my traffic, I'm going to pick this route. So you can actually use this to set the routers. Okay, router can only pick one location. For one destination, there's going to be one engine in a router. And similarly, the autonomous system is going to forward just one choice and to its neighbor. So for example, the autonomous system says, I'm going to pick this one. We will talk about the selection criterion, but I'm just going to pick this one as my choice. And once this one is picked, I will forward this path, of course, append my own number. So I'm going to send this 2, and then 3, and then the rest of them, and to this P. I'm going to send this new path and to all my neighbors, including to the other neighbors. And obviously, I will not send to a neighbor if their autonomous system number is already here. For example, I won't send this path to 3 because I got this from 3, so 3 is already on here, so it doesn't make sense for me to send it back. And if 1 is already here somewhere, let's say 1 is here, it doesn't make sense to send this back to 1 because 1 knows a shorter path to reach P, so definitely if this is useless. So if any of these things is already on the list, I will not send to them. It's useless. But if they're not on this, I will forward and to them. So now they have this path from me, and so they know that through me, and they can reach this destination and through these autonomous systems. And this table is going to be maintained because of this. Sometimes this autonomous system, they may update their path. And they may say, my path has changed. I'm sending you another update. If any of this get updated, and you're going to actually look at it, is this still the best path? If this is still the best path, and then you don't need to announce to anybody because you do not change your decision. But if because of the change and you end up picking another one, for example, now you're picking 4, and now you can actually tell everybody, I have a change, and you will send another update to your neighbor. So if your decision changes, and you will tell the other by sending an update to them, now they're going to actually update their information based on the new one. And sometimes the change has been made, you can no longer reach destination P. So for example, if everybody here tells you, I can no longer reach P, they actually withdraw, they call it withdrawal. Their route to P, because something happened on the internet, so P is no longer reachable, and so they're going to withdraw, and they're going to telling you, I have told you that I can reach destination P, but I no longer can reach them, so I am going to withdraw. So this is going to withdraw message. When the AS2 receives the withdrawal, it's going to still look at all its AS passes to see, do I still have a route to reach destination P? If I have, then I just need to change to that path, then tell my neighbors. But if I end up running out of choices, nobody can reach P, in that case, what do? I will just tell my own neighbors I'm going to withdraw the path, because previously I told you you can reach destination P through me, but now the network has changed. I can no longer reach that, so I'm withdrawing the path. So in this case, the AS2 is going to do the withdrawal. And you can see if a network gets disconnected and there's no other route, and to reach that, the enabling autonomous system eventually is going to find out. That's the main purpose of keep alive. If I don't receive the keep alive message from you, I'm going to know that the network is down. If I don't have other choice to reach you, I will withdraw. I will tell the rest of the world. If all the paths reaching you get disconnected and you are no longer reachable from the internet, then eventually all your neighbors is going to actually send out the withdrawal, and now eventually the entire world, they know they cannot reach you. And their packet is not going to be routed to you. In this lecture, we're going to look at how the autonomous systems select the best path. And we have talked about that an autonomous system will get multiple paths to the same network prefix from different neighbors. One neighbor give you one path. If you have 5 neighbors, you probably can get 5 different paths. So how do you select the best path? So you're not going to use all of them, and you're going to store them internally in your table. And because if one goes down, and you can still pick up the other one, so you have all of them in your table, but you're going to pick the best one, so you can use that one to set up your router, so that direction you want to go. And you're also going to announce that to your neighbors, the one that you have picked. What is the algorithm that pick among those paths? The BGP protocol specifies a series of criteria. Now the first one you're looking at is weight. You can assign the weight to different paths and through your local configuration. And so that's usually done through the administrations. So you're going to see I'm going to assign this larger weight and to this particular route. That's going to get you to pick this route, the route with high weight. And the next one is called the local preference. And local preference is also some kind of weight. I will talk more about that. After this local preference, and you're going to look at whether this is locally generated or is aggregated. So we're not going to dive too much into this. And so this is one of the criteria. And next one is one that is probably more intuitive. That is the shortest. You get the shortest AS length. The shortest AS length does not mean to be the shortest distance, because your AS could be huge, can have many routers internally, or your AS could be small and with a small number of the routers inside. And so this doesn't mean the shortest distance. But that's one of the criteria for you to pick the AS path. So we're going to look at some of them to see how that works. Before that, I'm just going to show you a real BGP table. And there are a number of these servers out there on the internet, and where you can telnet into, and you can look at the BGP table. And so this is the one that I'm using, and you can telnet into that server. You don't need to type the username and password. Once you're in there, and you can use a shoot IP BGP to look at the BGP table. It's a large table and many, many pages. So here, by looking at that, you can pretty much understand the structure of the table. So for this one, and you can see, and this is the prefix. So to reach this prefix, I have this 5 different paths. They are the same, but their routers are different. So you can see they have 5 different next hop routers. And there's a column called local preference and their weight. And the weight, they are all zeros, and there's no weight set in there. Local preference is not set either. And then this one, is whatever is picked. By looking at this one, we don't know what criterion is used because they all look the same. But I'm just using this table to show you the structure of the table. And in some of the table, and you would see the values in here, and that's going to affect how the path is selected. So here you can see there are 5 paths, and one is get picked. So let's look at the local preference. What is the meaning of local preference? Local preference is really just you set on the inbounding path. If you have a free inbounding path, like in here, I am AS2, I have these 3 inbounding paths. When I receive the inbounding BGP update message, I'm going to assign the local preference to some of them. For example, if I say anything come from this inbounding path, I'm going to assign 150 to that. The other one, I'm going to just assign 100. What does that mean? That means I'm going to prefer this path. If I get 3 paths to the same location P, this one says I'm going to get into P through this one and some other things. 3, 4. From here, this one, the local preference is 150. And that is larger than the others. This is 100, this is 100. So this will guarantee this one to be selected if their weight are the same. Because weight is the first criterion. But if their weight are the same, then the local preference is going to decide which one is going to pick. And so that allows the BGP routers to specify the preferred route. So in this case, this path from here will be further announced and to the outside world. And that's called the local preference. And one of the criteria, as I said, is called the length. So you pick the shortest length. Now sometimes if I am the autonomous systems, I have a multiple link, but one of my link is my backup. I don't want to use that link. I want to use the other link for the traffic to come to me. So in that case, I will intentionally make the path longer in one of the links. So for example here, if I just announce 118.72 and 128.230.0.0/16 to all of this link, the chances are the traffic could come from any of them. If I want to use this as a backup, sometimes you have a multiple link, but one of the link, you really don't want to use that because they have a low bandwidth, they have a slow speed. You want them to go to the other link because this is the primary one that you want to use. So how do you tell the entire world, don't use this unless this is broken? If both of them are broken, now of course you don't have other choices because they're going to withdraw. All of them, they're going to withdraw. And then the internet eventually is going to actually route the traffic to here. So that's what I want. But how do I achieve that? To do that, what you can do is you can announce through this link longer paths. You intentionally make this longer by prepending the same number 118.72 multiple times. So you're announcing this one to here. Now for the other one, you still announce the shorter one to here, to here. So now you artificially make this AS path longer along one of the paths. According to the selection criterion, that path will less likely to be picked unless these 2 other faster paths and they are broken. And that's how you can set up a backup. And you can see I'm looking at this server. I telnet to this server. I look at some of the cases and I can actually see a number of the cases here. So for example, for this network, and you can see this one get appended multiple times, and this one also get appended multiple times. And I don't know exactly what the reason is for this one, but chances are, and this is one of the backup paths, and they don't want you to go through this. But in this case, and you can see this is the only path. If you want to send to this, you're probably going to actually use this path to reach this one. That probably is the backup path. The other link, and they were either down or for some reason, and they were not available. In this lecture, we're going to talk about what happens internally inside an autonomous system. And this involves the internal BGP and also the interior gateway protocol. The one we have talked about so far, the pairing with the neighboring autonomous system and the protocol going between them, those are called external BGP. So you really talk to the BGP speaker outside the world. That's called external. But some of the autonomous systems, they have multiple BGP speakers. They actually do the pairing with other network in different places, in different cities. So they will have multiple BGP speakers. So how do they exchange information? So you can see in this case, I have AS9, which is large ISP. So it has multiple BGP speaker and talk to the outside. Now internally, they will forward information that they collect from here. They're going to forward that to the other one, because to the outside world, they only see this AS9. So AS1 will know that you can reach the AS2, AS3 through the AS9. So how do we communicate that? So internally, this BGP speaker, they are actually use iBGP, internal BGP protocol. They're going to connect to them in a full mesh. So they're going to fully connect it. Each of the BGP speaker is going to connect to all of the BGP speaker inside the entire autonomous system. Whatever the information they get from outside the world, if they pick the best path, they are going to use the iBGP to forward this to its pairs internally. Now the only thing that is different is here is if I forward this path to the outside world, I'm going to add myself at the front. Right? If I'm sending to you on the AS path, my number is going to be at the front. But if I'm disseminate internally to my internal pairs, I'm not going to add this number. Okay, so when they actually send this out, they're going to add this number, but I am not going to add this number because we are internal. I'm just forwarding whatever the information I receive from this end. I am going to forward that to you. Of course, I'm select the best one to forward to you. I don't forward everything to you. And that's called iBGP, really just for the BGP speaker inside the same autonomous system and to really synchronize with each other. So even though they are in different locations, but they're going to actually pull their information together. And so they know that my autonomous system can reach many different autonomous systems, even though this BGP speaker here does not directly connect to the BGP speakers outside, but they're going to actually share the information internally. The iBGP is still the BGP protocol for the BGP speaker and to communicate. Once the BGP speaker collect the information, and they will have to inform their internal routers. Each autonomous system, they have many routers depending on their size. Now, all the information collected from outside need to be disseminated to this internal router. BGP speakers know the map. The internal router, they do not need to know the route. They just need to know the direction. So once you collect all the information, you're going to actually disseminate the information, usually through a different protocol, different routing protocol. So interior routing protocol usually are different from the BGP. For example, the two of the popular protocol is called OSPF and RIP. And those are the protocols running inside the internal routers. So the information collected from outside will be fed into this routing protocol, and that the routing protocol is going to help these routers and to set up their routing directions. And that's how the BGP routing protocol, which is the routing protocol performed by the BGP speaker, they're going to collect the global information. Once they collect the global information, and they're going to actually disseminate that internally through another routing protocol, interior routing protocols. And that routing protocol is going to set up their routing internally. Now, different autonomous systems, they can use their own routing protocol. There's no standard. But outside the world, in the BGP, everybody has followed that standard. And so they can exchange information. And that's how the internet actually functions. That's how the routers, all the routers, and they get configured. After all these routers get configured, now the packet can go from one router to another router. At every router, and there's a sign going to this network go here, this network go here, and so eventually, and they will actually arrive at the final destination. So when the network changes, the BGP will get information. That change will further disseminate through the internal routing protocol. That will change the sign. So next time when a packet gets to this router, now the direction could be different. So this is how the whole world works together and to set up the routing. In this lecture, we're going to talk about the overlapping routes. And we're going to see how the BGP deal with overlapping routes. So let's take a look at an example. What is overlapping route? Overlapping route basically means these two network prefix, they are not complete disjoint. And one is a subset of the other. You actually see this quite often. And here's an example. This comes from our BGP table in one of the routers. And so you can see these two network prefix /20 and /19. This part are the same, this part. If we actually convert in these to binary, so 128, that is the 1000 and 0000. And this is 128. The /20 means the first 20 bits are the network ID. So this is 16. So for the /20, that will be this part. And for /19, that will be this part, 19, and this is 20. Let's see, I have a IP address 41.214.128.5. This IP address is going to match with both of them. Because of the network ID part, it's going to match with this, it's going to match with this. So there's two matches. But now which one is going to be selected? Here's the rule. If you match with a multiple network prefix, the most specific one wins. So in this case, I have two matches, but the second one with /19, only the 19 bits is a network ID, so the number of bits match is 19. But for the /20, the number of bits match is 20. So in this case, this /20 is going to win. For this one, we're going to take this route because this is selected. You can see this route is going to be selected. So this path is selected. So for this one, I'm going to pick that one. Now if I have another one, let's see, I have a 41.214, and then I have a 1 at this bit. I'm putting 1 at this bit here. This is going to be the 16. If I'm writing 144.5, if I have this IP address, now let's see which one is going to match. 144 is going to be 1001 and 0000, and this is 128, 64, 32, 16, so that's 144. Now this one you can see is going to match with 19 only. It's going to match because the /19 is going to have a match, but it's not going to match with /20 because /20 says this bit is also network ID, but I need 0 to be here, but you have 1. So in this case, this one will be matched because this is the only match. And this one matches with both. So when you have this overlapping net prefix, and you can look at how many bits are matched, and for each of them, and you pick the longest one. Okay, so the BGP doesn't have any issue with that because of this rule. Now, why do we use this? Why do we create this scenario? And there are a lot of actually interesting applications for this overlapping network prefix. So one of the applications is called globalization. So if you have this network in different locations geographically, and you want to still using the same network prefix. So for example, circuits here, we have a 128.230.0.0/16. This is a network for the circuits. And Syracuse University also have a study abroad program. So let's see, we have a UK. We have a UK office. So we want to use the IP address 128.230.5.0/24. I want to use one of the subnet in here. How do we make this to work? Now this network got geographically split into 2 different places. How do we make it work? With BGP, and you can easily make it work. What you need to do is you just need to announce that network from where you are. So for the UK, and you just announce that network and to the entire world, to telling the entire world in order to get to that network, and you have to go through this particular AS path. Now at the Syracuse, you can announce this bigger one, the /16, and you can actually announce also that to the entire world. Now let's see, somewhere in Morocco, this is P1 and P2. So I'm going to get a P1, and I'm going to get P2. I'm going to get this 2, and this one path, and there's another path. And these 2 are overlapping. So now if I want to send a packet to 128.230.5.4, if I want to send this to this address, and there will be 2 matches. It's going to match with this one, P2, with 24 bits, P1 with 16 bits. So this one is going to be selected if you want to go to here, and then you're going to, the traffic will eventually go and send it back to here. But if you want to go to 128.230.4.5, in this case, and there's no match for this one. The only match is the 16. So the traffic now this way will be routed through a different path, eventually get to here. There's no conflict at all. And the BGP will nicely solve these overlapping problems because they're going to have a different path. They're announced in different locations, they're going to end up have a different AS path. So the way to reach them and will be different. So this actually allows a company, if they have this office across the globe, and they can use the same network prefix, they just need to divide them into subnet, and they're going to actually announce that from different locations. And for the larger one, and they will just announce that from their headquarters. So if it doesn't match with any of the subnet, they will eventually come to the headquarters. And here's the example for the Facebook. And the Facebook is actually divided its network into many different subnets. And if you look at here, and this is a route I got, and this is only a subset of a route, and Facebook has many different actually IP prefix announced by Facebook. And you can see, and they're quite overlapping. For example, this one, /18 is larger than the /19. It covers everything here. /24 is actually, all of this are covered by this route. But they are in different locations. If you look at this one, 78 is in Virginia. The 80 is in the Ontario, and this one is in Madrid, Spain. These IP addresses are located in different places, even though they belong to the same Facebook network, but they are geographically distributed across the globe. This way, people in Spain, if they want to access Facebook, the chances are they're going to actually reach the server nearby. This is called deaggregation. You deaggregate your network into small pieces, and each of them could be in different locations. Now, BGP naturally supports that. Now, one of the downside of that is this is going to actually make that BGP table larger. And this is going to actually cause a lot of issues because of some of the BGP routers and the total number of the engine they can put in the routers can be exceeded. They cause a lot of trouble. And also because of the size of the tables, if it's larger, and then performance is going to be affected. Another reason for the deaggregation is for the load balancing on the links. So in this example, if I announce the same thing 128.230.0.16 to all of this link, it could be possible that all the traffic will eventually just go back from one of the link, because if the choice over this one wins, and then all of traffic will come from here, that's going to congest this link. What if I want to distribute my load? So I want this one to get some, this one to get some, this one to get some. So what do? I can use this deaggregation. I can announce 128.230.0.0/16 to here. I can still announce to here, but I'm going to announce the 128.230.128.0/17, and you can see 128, that's one more bit. I'm using 17 and to this. So I'm announcing this one to this and to this. And so now you can see if the IP address matches with this one, and they're going to come from here, they will not come from here, because this will be selected and over this more general, the net prefix. So they're going to come from here. Now the rest of them will come from the other places. And so you can see by doing the deaggregation, now I can distribute my traffic and over different links. I actually look at the announcement made by the Syracuse University, and the network 128.230/16 get deaggregated to many different subnets. And I don't know exactly what the reason is. Some of them could be the geographic location, because Syracuse University has the office in New York City in different countries. So this could be one of the reasons. The other reason could be because of this load balancing, but I did not know exactly the reason behind that. But from outside, I can observe this deaggregated, the IP prefix announcement made by the Syracuse University. And you're going to find out many networks, they did similar things. In this lecture, we're going to talk about IP Anycast. IP Anycast is one of the ways to achieve load balancing. So load balancing means if I have a same service, but I want them to be processed by different computers. And there are two typical ways to achieve this. One is to use the same name, but the same name could be mapped into different IP addresses. So basically, you rely on the DNS to map the same name, for example, www.facebook.com, into different IP addresses. And that can be done because Facebook's DNS server can dynamically pick an IP address when you ask for the IP address for that name. And this is one way. The other way is to run the same server on different machines, but all of these machines have the same IP address. The question is, how do we allow these multiple computers to have the same IP address? Will that cause any problems? And this is called IP Anycast. So IP Anycast is naturally supported by the BGP. So let's look at how the IP Anycast works. IP Anycast is used by the root server. We talk about some of DNS root servers, like F root server, and there's only one IP address for the F root server, but there are many different computers running F root servers, and they are across the globe. The underlying technology is called IP Anycast. Let's say I want to run the DNS server. I want to run a server here. I want to run a server here, here, and here. I want to run them, but there's only one IP address I want to use. Now all of this, and they're going to be announced that same IP prefix and to the outside world. So they're going to announce this. They're going to say, I own this IP prefix. They're going to announce this to the entire world. So let's see, this is the AS10 is this belongs to, 10 is this belongs to. So they're going to announce to their neighbors. Let's see here, we have a neighbor, only one neighbor. Just simplify this. This AS1, and this AS2, AS3, AS4. So they can just announce to their neighbors. Now, if you are anywhere, let's say you are here, and the chances are that you probably will receive the AS pass from all of these places. So you will here, you will receive the AS pass to this IP address, and you're going to have this bunch of things here, and then it says from 1 and 10. And you're going to get something similarly and saying this, and the 2 and the 10, and 3 and the 10, and the 4 and the 10. The chances are so the autonomous system here may receive all these passes. That's very natural. Whether you announce that from one location or you announce the same IP prefix from different locations, chances are you will have a multiple path. The BGP do support a multiple path. Now, this autonomous system, once they see these 4 passes, and what they're going to do, they're going to pick the best one and then to announce to their neighbors. As we said, there's multiple criterions here. Now, one of the criterion, the easiest one to understand, is the shortest one. So now you can see from here in South America, the path of each of this, their length could vary. Now, if this one is closer to the here, now this path could be shorter. And so you may end up picking this route. So if you trying to visit this IP address and you would actually send your traffic here. But now if you imagine you are in Africa, you are in here, your autonomous system in here, you will see the similar things. You're going to see multiple AS passes. But this pass, the second one, because you're closer to here, this one is likely to be shorter for this autonomous system. So if any of your customer trying to send a request to this server, or this server, or this server, the same IP address, the chances are, and you're going to actually send to here because of this is shorter. You're unlikely to send to the other one. And so you can see this BGP naturally allows that. And this is another special case of overlapping IP address. It's just now in this case, the IP address now exactly overlapping, and they are announced from different locations. They announce exactly the same network prefix. But for the BGP, they don't care whether they are announced in one location or they originate from multiple locations. For them, they're going to see the multiple paths for the same IP prefix. And they're going to use their algorithm to select the best one. This could be the one going to the US, could be going to the Europe or Asia. Really depends on where you are. That's actually can naturally achieve the load balancing and also the proximity. So if you're local to a server, chances are they're going to actually talk to the server and nearby, and this make it faster. This is widely used for the DNS root server. DNS is the infrastructure of the internet. So the faster you can reach the root server, the better the performance is. And therefore, there are certain DNS servers, they are all identical. And for many of them, like F-root server, they even have many computers distributed around the world and using the IP Anycast. IP Anycast means as long as I can reach one computer and my request can be satisfied. Okay, so that's called IP Anycast. It's different from the broadcast. Broadcast means you gotta reach everybody. We want to be able to reach anybody. BGP is going to actually select the best one so you can arrive at one of them. You will arrive at one of them, depending on where you are, and decide which one is going to be picked. But you're going to arrive one of them. That's called Anycast. You can arrive any of them. All of the DNS server, they're going to have the same data. As long as you talk to one of them, you will get the same result. IP Anycast provide a very nice load balancing. So if you have a service and that requires load balancing, and these are definitely techniques that you can use. But just keep in mind that the BGP routing, they are dynamic. They cannot guarantee you will always pick the same computer. At this moment, you maybe pick this one. Next minute, the situation can change, you may pick the other one. So if you send the packet and you won't be able to guarantee you're going to send to the same destination. At this minute, it's going to send to this one, at the other minute can be sent to the other one. So that makes this IP Anycast not appropriate for the TCP, especially a TCP connection that can last long. It's very useful for the UDP based. It's not connection based. I'm sending a request, I get a reply. Next time I'm sending a request, I don't care about whether I send to the same server or a different server. There's no connection. And that's why for the DNS, it's a very good application because DNS based on the UDP. But if you want to use IP Anycast for TCP, you need to know that you won't be able to always talk to the same server. And so that's why if you look at this question, if I want to run a web server and using the IP Anycast, can I do that? Really, this depends. Some of the web servers, they do use IP Anycast because web server itself is stateless. Even though every request is done through the TCP connection, but once you get your request, that connection is going to be broken. And then next one, and it's going to be another connection. So if the connection is short-lived, and you can still use IP Anycast because within that short period of time, with high probability, your packet will go to the same server. So that's still workable. But if you have a long-lasting connection like Telnet, and you want to use IP Anycast for the Telnet service, and that's definitely not a good idea. Because while you are still connecting to this server, now the routing changes. So your next packet now is going to be routed to a different computer. That computer says, I don't have a connection with you, so I'm going to reset you. and therefore your connection is going to be broken. So that's why the IP Anycast is primarily used for the stateless, connectionless type of service, and not appropriate for the TCP connection that lasts for long. In this lecture, we're going to talk about some of the very useful BGP tools and utilities, because it's very hard for us to access a real BGP speaker. So in order to gain the hands-on experience, we got to find a different way to do that. Right now, I'm actually developing an internet simulator where I have BGP speaker inside the simulator. It's going to take a while for me to finish developing that simulator. So before that is finished, we have to rely on some other tools to learn the practical side of the BGP. Fortunately, there are a lot of tools that we can use. So in this lecture, we're going to look at some of them. And I find this RIPE.net is probably the most useful place. It actually plays a lot of BGP collector across the globe. So they are more like the BGP speaker, so they can peer with the others and they can get the BGP update information. They're not going to forward that. They're simply observing the AS path. And they put all the data together, aggregate them together in RIPE.net, and RIPE.net provide a list of the tools where you can use to do the query and to visualize data. So that's actually allowed us to look at the real BGP data. And this is one of the tools that I use very often. If I have an autonomous system number, I want to find out who is pairing with this autonomous system. Who are these autonomous systems' neighbors? And you can use this neighbor widget in RIPE.net and to figure out the neighbors. For example, in this case, I trying to figure out the neighbors of the Syracuse University's autonomous system. I found 3 of them, Cogent, Level 3, and an ISONET. And also I tried on the Google, and I find out Google and pairing with 345 autonomous system. So that's a lot, but that's Google. Google want the customer to reach them faster. So they want to reduce the distance between the end user and their server. So how do you do that? If you only pair with a small number of the autonomous systems, then across the globe, people have to travel through several autonomous systems in order to get to your neighbors and eventually get you. To shorten the distance, and you can just go to place closer to your customer, and then pair with their autonomous systems. So this way, an end user can reach you in a shorter distance. And this is a very common practice. Some of the content delivery network, CDN, and they use these techniques. For example, Akamai. I look at Akamai. Akamai also has more than 300 peering numbers. Because Akamai, they trying to push your content closer. So they are third-party companies. If you have a content, you want your content to get closer to customer. If you're Google, you can do that by yourself. But if you're not Google, you're a small company, and you can use this CDN network, which can push your content closer to your customers. And they are using similar techniques. They just deploy their server and across the globe, and they pair with a lot of autonomous systems, so the end customer can reach them faster. If you want to know what prefix are announced by autonomous system, and you can use this widget. So here I'm using this one. I can find out the prefix announced by this autonomous system. I'm only showing you a shorter list, and the actual list is longer. And from this one, you can see the Syracuse University not only just announced the /16 address, 128.230/16 belong to Syracuse University, but it announced many, the 17, 18, 19. As we mentioned before, there are many reasons for that. Globalization is one reason, load balancing is another reason, There could be other reasons that lead to the fragmentations of the network. Sometimes you want to know the AS path at a particular location. So you want to know how the announcement you made from this autonomous system get propagated across the globe. And you can look at some of these looking glass. So those looking glass are the BGP collectors, and they get deployed across the globe. So you can actually look into what they see. For example, in using this widget, I can find out who have observed this network prefix. I got these 9 engines. So these 9 different collectors, and they have observed and this IP prefix. If you click on this, for example, I click on the Amsterdam, and I can find out the actual path is from 11872. That's the origin of this IP block, and go to this, and you go to here, and you see some of the more details. And you can also look at the Germany, and I did not list all the 9 engines. And this is quite useful. So this allows you to look at how your network prefix get propagated throughout the entire world, and you can see observation from different places. And this is one of my favorite. And this one allows you to see the AS passes. It visualizes your AS passes. So here you can see this is Syracuse University 11872. It's too small, but if you run this widget, and you can easily just zoom in, zoom out, and you can drag those nodes into different places. And it's interactive. And these are the 3 pairs of the Syracuse universities. All of these are the AS paths observed by the collector. So you can see from here to here, and this is one of the paths. So you visualize the path, but not just statically. And you can play this. There is a play button here. If you click on this play button, and this one is going to actually visualize the AS path over the time. So if at some point a path gets withdrawn, it's going to show you that this path gets withdrawn. It has animation. So it's very, very useful for you to understand the changes of this AS path throughout certain period of time. I see some of the analysis that use this tool. Sometimes when you have an attack, they want to reconstruct the attack. They want to see what exactly happens during that period when somebody attacked the BGP. So by looking at the announcement related to this attack, and you can visualize them, and you can see how these attacks affect the redirection of the AS paths. So it's very, very useful. Those tools allows you to look at the data collected by those BGP collector. What if you want to access a real BGP speaker? And there are certain open BGP routers which allows you to log in them, or some of them, they provide the web interface. So you can put your command in the web interface. That command can be executed by those BGP speakers. For example, here I can telnet into this server, and this allows me to see the BGP table. Once you're in there, and you can type the show IP BGP, that's going to show you its BGP tables for every IP prefix, and it shows you all the engines associated with that IP prefix. We have seen this before. And also it also shows you the selected path. So that's very useful for you to look at a real BGP speaker. This is just one of the examples. There are several other open BGP speakers for you to look at. Here's another command line tool that you can use in your Linux, and you can just simply use whois to find out the IP address, the network prefix announced by certain autonomous system. So here I'm trying to find out the announcement made by this autonomous system. So I'm using this database, whois.radb.net. I'm running this command. I'm typing this query string. And this is going to give me all the information regarding this one. I'm only interested in the engine that has this keyword route that gives me a list of the IP prefix announced by this autonomous system. You can also get the autonomous system number from the IP address. So if I see an IP address, I want to find out who owns this, and you can use the same database and you can do a query. This one, it says belong to Facebook. Here's another example. I know who owns this. That's Google's DNS server. And you can do this query and you're going to find out, and this is owned by Google, and here's autonomous system numbers. So this comes very handy. So sometimes you want to get IP address from autonomous system number or from the autonomous system number to get an IP address, and you can easily use this tool and to get those information. And these are some of the tools that I've been using. I found them useful. I have gained a lot of insight just playing with those tools. You should also try those tools, and so that can enhance your understanding of how BGP works. BGP is very sophisticated. By using those tools, you can definitely get more insight into how this system works. In this lecture, we're going to look at the attacks on BGP. BGP is a very essential element of the internet. It is a glue of the internet. It glues many different networks together to form the internet. Without the BGP, or if your BGP breaks down, then the internet is going to be many isolated networks within the network, and they can communicate with each other. But across the network, they won't be able to talk to each other. Because of that importance, so BGP is very essential, and obviously it's going to be the primary target of the attackers. In this lecture, we're going to mainly focus on one particular type of the attacks. It's called a prefix hijacking attack. The main idea of that attack is to be able to hijack a network prefix. For example, if this network prefix belongs to certain entity, if you want to hijack that, so you can redirect all the traffic to you, and then you can drop that, or you can make modification to this traffic. And so that's called the prefix hijacking. The main idea of the hijacking attack is very, very simple. If you understand this overlapping IP address that we talked about before, so if we have this overlapping network prefix like this, 1.2.0.0/16, and this is network prefix. But if I have another one, 1.2.128.0/17, 1.2.0.0/17, if we just convert in these to binary, so we have 1000, and here we do the 000. 17, we already have a 16 bits here, so 17 is going to start from here, and this is 17th bit. If I have an IP address, I have a 1.2.0.5. If these three engines, these 2/17 and 1/16 are both in the routing table, now if I see a packet going to 1.2.0.5, it's going to match with two engines. First engine is going to match with this one, because the first 16-bit of this is the 1.2, is going to match with this with 16-bit of the matching. It's also going to match with this one, because there's 0 here, and so that's 17 bits of the match. It's not going to match with this one because this bit says 1, but you have a 0 here. So it's going to match with this one. So the first match is here, the second match is here. So you have two matches. Which one do you pick? Remember, we talked about the rules. The longest one is going to win. The more specific route is going to win. So in this case, the /17 is going to win. So basically, if the 17th bit is 0, and you're going to pick this /17 engine, if the 17th bit is 1, you're going to actually pick another /17 one. You're never going to pick the /16, even though it's in the routing table. But for any packet going to 1.2. anything, either it's matched with 1/17 or 0/17, and they're going to win. Basically, if somebody announced this /17 network prefix, the original one, the /16, is going to be useless because no router is going to use that. And that is called network prefix hijacking. So the attacker basically announced this. So this is target. This is what we want the victim. The victim have announced this one, but I want to hijack this entire thing. All I needed to do is to announce these two more specific route. If my neighbors propagate that and throughout the entire world, then everybody in the world, every BGP speaker in the world, and they're going to see that, and they're going to set their routing tables. And therefore, when they route a packet, the packet will eventually route towards me, and I can just drop the packet. This is so-called black hole. If you want to hijack all the traffic going to a particular network, and you drop that, and you pretty much black hole that network, so nobody can reach that network. They can still send the information out, but nobody is going to be able to reply to them because all the reply is going to come to you and get dropped. Just show you some of the things that I did in my simulator. I've been building my simulator, so I can actually try different attacks without affecting the outside world. Here's a BGP update I sent out. This definitely is attack. I'm announcing this. I want to hijack 172.217.0.0/16, and this IP address belongs to Google. So if in the real world somebody want to hijack that, want to black hole the Google server, all they need to do is to announce it to prefix. Just like in this case, I'm announcing /17/17 from this autonomous system, and this is made up autonomous system. And so I'm observing this from one of the autonomous system inside of my simulator, and you can see the AS path is here. And then I'm going to one of the autonomous system to look at its routing table. On here, I see 3 entrants here. So on this routing table, without these 2 entrants, anything that going to this network will go to here, will go to 199.109.9.94, and eventually, and this will go to the Google node and in my simulator. But once I have that one, and you can see if anything going to 172.217, let's say I'm putting 0.5, if they want to go to here, now one of this is going to actually have a match. So in this case, and this one is going to have a match. The router is going to 109.9.5. Now the traffic will not go to here anymore. It will actually go to this engine because this one is going to win, even though this engine and this engine, they both have a match. But this one has a longer match, 17. So the packet will be routed to here and eventually will get to my AS65000. And that's my attacker's autonomous system. You can see by doing that, you can cause this router and change their routing direction. So instead of routing to the intended destination, now they're going to route towards you. You can drop the packet. That is my simulation. My simulator is in a contained environment. I'm still building this simulator. Hopefully in a year I can get it ready so other people can use my simulator and try these different BGP attacks and defense mechanisms. To test whether you understand this attack or not, so let me ask you this question. So here Bob is a student in my class, and he failed my class. But he was not happy. He wanted to take a revenge. So he wanted to black hole the Syracuse University 128.30/16. The question is, can he do that? So I will leave you a few minutes to think about whether he can do this or not. Okay, so if you think that he can do that, and you just insulted me, because Bob just failed my class. How can he do this? He doesn't even know how to do that. Okay, so, but that's a joke. Okay, so technically, of course, he can do that, and we just use the similar ideas. And Bob just need to create an autonomous system and pairs with some of the neighbors. And as long as the neighbor allows Bob to announce that prefix, and eventually that network prefix is going to be actually reach the entire world. So he only need to announce 2 of the network prefix. 128.230.0.0/17, 128.230.128.0/17. And that's all he needs to announce. And these 2 network prefixes are going to actually cover the original one announced by 128.230.0.0/16. I assume that Syracuse only announced that /16. In practice, Syracuse announced much more than that. So in the real attack, if you really want to do that, you will have to announce more than that, not just /17. Okay, so that's the technically how that works. But obviously, if you failed my class and you don't know how to do that, so if your answer is yes, and you should give me 5 push-ups just for your punishment, then you can leave a comment in the feedback field of my course and tell me whether you have done the push-up or not. Okay, just be honest. So the attack on BGP is quite severe, and you can see by simply just announce these 2 fake network prefix, and you can black hole a network. A situation like this happens a lot. Okay, mostly because of the misconfiguration, not because of the intentional attack. We're going to talk about some of the case studies. The question is, how can we defend against BGP attacks? The network prefix hijacking is just one of the attacks. There are several other attacks. There are attacks against BGP speakers. BGP speaker is just one computer. If somebody can attack that, bring the computer down, or just penetrate into the BGP speaker so they can control the BGP speakers, and then they can cause damage. So you got to protect your BGP speaker. Well, you also need to protect your BGP session. BGP session is just a TCP connection. We also learned from the TCP module, you can launch the session hijacking, you can do the spoofing, you can do the resetting. You got to protect that. Encryption, encrypt your TCP session, but the reset attack can also break an encrypted session like SSH. In the TCP module, we talked about that. So how do we prevent the reset attacks? And there was one very practical solution. You can look at the TTL. Remember the time to leave field. If attacker launched the attack from remotely, it doesn't matter what they set for their TTL. Every router is going to actually reduce the TTL by 1. Once they reach that destination, their TTL will not be 255. And that could be very useful because a BGP speaker, they are physically connected. They're only one hop away. Because they are pairing, they are in the internet exchange point, they are physically located together. So you can set your TTL to the largest, 255. When the receiver gets a TCP packet, and they can look at whether TTL is still 255. If it's not, then this packet comes from a remote place that should be dropped. Okay, so that is something that you can use. Very, very simple way to prevent the attack from launching the attack from the remote place. Regarding the fake update, fake announcement, and that is quite difficult to defend against. Now, one of the ways to do that is you gotta enforce some of the filtering rule at your boundary. You should not just accept all the announcement. You should actually decide what to do with some of the announcement. There's a lot of the filtering rule that you can apply. I'm not going to dive into that. If you look at that RFC, 7454, and you can see some of the recommendations described in the document. So the main idea is you gotta enforce some of the policy, just like a firewall. You should not just accept all the announcements. You gotta decide which one is valid, which one is not valid. Okay, so those are something that you have to do. The fundamental problem of the fake BGP update is integrity checking. So if I don't own certain network prefix, I can still announce that there's no mechanism to verify the integrity of that announcement. So to completely solve that problem, we need to enforce integrity checking. We need to have a mechanism and for people to check integrity. Public key certificate, PKI could be used to solve this problem, but it's very, very non-trivial. So the BGP is quite complicated. So remember, we talked about the same IP prefix can be defragmented. And also, to reduce the size on the table, many BGP speakers, they aggregate the network prefix together if they have the same AS path. So that aggregation is going to cause a problem because when they aggregate that, they create a net prefix which is not owned by anybody. So how can you verify the integrity of this announcement? So the situation is quite complicated. So I'm not going to talk too much about this solution. This is a very active research area, and you can look at some of the discussion, research paper to gain better idea on the solution to this problem. Another thing that you can do is if you are autonomous systems, you should actively monitoring the BGP announcement. If somebody try to hijack you and they will make the announcement, that announcement will be broadcast to the entire world. Eventually, you will be able to see that. So if you have active monitoring, you will immediately detect the problem and you can act on that. For example, you can contact the ISP. You can contact the autonomous system in their neighbors. If somebody send out a fake one, you communicate with them. If it's a mistake, they will correct the mistake. If this is intentional, talk to their neighbors. Their neighbors will look into that. They may block that announcement. Okay, so there's something that you can do by actively monitoring the situation. So you know when somebody's hijack your network prefix, and you can immediately detect that and you can have solutions. So those are some of the things that can do. We did not dive too much into this. We only give a very brief discussion of the countermeasures, and the actual defense mechanism is out of scope of this lecture. In this lecture, we're going to look at some of case study of existing BGP attacks. These attacks, they are not intentional attack. They were caused by mistakes. But in terms of consequence, and you will see the damage caused by those unintentional attacks. We're going to look at two different cases, and they are quite interesting. So one case is Pakistan hijacked YouTube around February 2008, and there were some of the videos on YouTube which were offensive to people in Pakistan. So the government decided to block YouTube. The technique that the government used is to hijack YouTube's IP prefix. But the idea is to announce that network prefix internally inside the Pakistan, not to the outside world. But somehow, because of the misconfiguration, the announcement by their autonomous system get announced to the entire world. So what they actually did is they were trying to use exactly the same idea that we talked about in the previous lecture. They announced a more specific route. Before the attack, YouTube announced this one. YouTube announced many different networks, but this is the one that was under the attack. So the /22, and this was announced by the YouTube. But around 1847, this autonomous system, that's Pakistan Telecom, announced this one, and this is /24. This one covers 208.65.152.0 and also covers 50. And this one actually covers these 4 of this because it's /22. If you actually extend that to 24 bits, that consists of these 4 of this /24 network. The Pakistan Telecom announced this one, which is this here. As a result, we can see that if any traffic going to this network, they will match the announcement by Pakistan. They will also match the announcement by YouTube. But as we said before, this 24 will win. And therefore, anything going to this network will be routed to Pakistan. And that's where it will be dropped. The AS17557 is pairing with AS3491, and that's PCCW Global in Hong Kong. So this is the neighbor, but this neighbor did not check the validity of this announcement, so it actually broadcasts to the world. That's how the entire world sees this. And if you look at the one of the picture here, and this is actually is from the ripe.net, and they have done the analysis of the event. Right after the attack, for that IP prefix, and this is YouTube, there was no connection. No traffic is going to go to YouTube, and all the traffic is actually going to Pakistan because all the paths, all the routing is going to actually use that more specific IP prefix. So in terms of that IP prefix, YouTube will get isolated. So that is the result. And YouTube have been actively monitoring the situation. So they actually detect the problems and it try to fix the problem. And it's trying to communicate with PCCW and with Pakistan Telecom and try to resolve the issue. But that takes time. So while waiting for the situation to be resolved, and YouTube try to hijack that back. So what they do is they announce this one. So they also announce /24, and I don't know why they do this, and this definitely is not the best way to get this back. They announced exactly the same /24. So Pakistan announced /24, and you announced /24, and both engines, there's no clear winning or losing. So really depends on other criterion, right? We talk about the local preference, we talk about the shortest path. So if the shortest path is going to use the countries near Pakistan, they're going to select the Pakistan as destination. Countries near where the YouTube is, the US, is going to actually select the one announced by YouTube. So really, it doesn't actually get everything back. And so that was announcement by the YouTube. I assume that's probably some of the mistake made by YouTube. But immediately they actually correct their mistake. They now announce more specific route. So only 10 minutes later, they probably realized that was not a good idea. And they announced /25. And they used one more bit. So 128 and the 0 here. But they are using the /25. That is going to actually cover this range. So now with this one, if the packet going to that particular server, and they will use the new net prefix announced by YouTube. So now YouTube successfully get it back. Okay, but that's before the problem get resolved. That's something that you can do. That actually looks very interesting. And eventually, through the communication, the PCCW realized the problem, and they withdraw the route originated from Pakistan. So even though Pakistan can still announce that, but its neighboring ISP, the PCCW, is not going to announce that. They actually withdraw all the paths from there. And this diagram shows that after the problem gets resolved and this one gets isolated, in terms of that network prefix, and this one, nobody actually go to this autonomous system. This is Pakistan, and all the traffic is now going back to YouTube. So that's very, very interesting, the way how the attack was launched, and also the way how YouTube tried to get it back. The first time was not the best idea, but the second time, and that works. And eventually the problem gets resolved because it was not intended to be like that. It was a mistake. So the problem could be solved quite quickly. Here's another case which is also quite interesting. This time involves Twitter and Turkey. The reason was similar. There's some tweets in Twitter that was offensive and to Turkey, and so they decide to block Twitter. Now, what they did is they were trying to use the DNS, because when people from Turkey, they were trying to reach Twitter, the first thing they need to do, they need to find the Twitter's IP address. So since the government control the DNS server, so they simply just change the DNS engines in the server, so map the IP address to something else. Now nobody can access Twitter. But quickly people inside Turkey realize this DNS server doesn't work anymore, but there are plenty of other DNS servers that I can use. So people start to switch to other DNS server. They go to 8.8, which is Google DNS server, and this one is provided by another company, OpenDNS, and this is one provided by the level 3. All of these are global DNS server, and you can just ask them for the IP address for Twitter. So the change is very simple, and you just change their local DNS server setting. And of course, the government quickly realized that issue, so by blocking the access through the DNS is not going to work. And that's when they said, I'm going to block those DNS server. Now, instead of setting up the firewall to block that, the government decided to use BGP to hijack those networks. And similarly, the idea was to announce those hijacked network prefix to the inside of Turkey. So they will redirect the traffic to the autonomous system that actually announced this fake prefix. That was the intention, but somehow that didn't work out that way. The BGP announcement get out, and that gets spread to the entire world. The particular network prefix they actually use is the /32. And they basically announced /32 for these 3 DNS server. And obviously, you're going to actually hijack all of them because /32 is the most specific prefix you can have in the IPv4 space. So they successfully hijacked those DNS servers. But unfortunately, everybody in the world, now they're going to pick this route. When they need to visit this 3 DNS server, a lot of computers in the world, they rely on this 3 DNS server. Now they're going to pick the route towards Turkey, and will the DNS request get dropped. So that actually pretty much hijacked those global DNS server. In terms of attack, that was quite successful. And again, this is a mistake made by the operators, and eventually they fixed the problem. But that demonstrates how easy it is, if you own an autonomous system, how easy it is to launch the attack. Imagine you use the same technique to launch the attack on the root DNS server, the 13 IP address of root DNS server. If you use a /32 and to make that announcement across the globe, now everybody's going to actually use you as the DNS root server. And that's the root of the DNS query. So if you can hijack that, you bring down that one, you can also break down the internet. Other than this attack on BGP, there's many of the cases where the physical cable were broken. It could be human error, could be a natural disaster, earthquake. earthquake can break on the ocean cables, and that can cause a problem because most of the on the ocean cables, they connect the continent. So those are the major cables. A number of years ago, there was an earthquake near Taiwan, and that breaks the trans-Pacific cables between the North American and Asia. So that cable get broken, and that disconnect internet service between the continent. In this case, you see that the ship's anchor actually sliced the internet cable under the ocean that cut off the access of 6 African countries. There was one interesting article written regarding how you can destroy the internet. So that was very interesting to read. If you look at that article and shows you a lot of places where you can see those cables. So it has a picture. For example, here it shows you this is one of the cables, and here there's another cable here. It even tells you the location of those beaches and where you can find this cable. So that's how vulnerable the internet is. If somebody really wants to launch the attack, and they can just take an axe and go to there and dig out the cable and break the cable. That shows you all the possible attacks that can be launched against the internet. But fortunately, these days, internet get more and more connected. So there's not just one single cable, and if this cable is down, the BGP protocol is going to automatically adjust to that. They will redirect the traffic. So if one cable is broken, the speaker on the other end, they're going to find out that this network is not working. They're going to withdraw the route, and that's going to cause the internet and to redirect the traffic. If these two networks are still connected through other route, maybe they're going to take a detour, but still, and they can get connected. So because of this redundancy, so even if you cut one cable, the internet is still going to be function unless you cut all the cables, but that's going to be much, much more difficult. Let's summarize what I have learned from this module. In this module, we have talked about how the internet are glued together. So internet consists of many of the autonomous systems. In order for internet to work, and they have to be connected. And that's called the peering. After this network are peered together, and they're going to set up the BGP session so they can exchange the routing information. They can also route the traffic from one autonomous system to another autonomous system. We talk about how the BGP works, how the network prefix get announced, how the AS paths get propagated, and how each BGP router select their best route. We also talk about the IP Anycast, so how the BGP support IP Anycast. And then we talk about the attacks on BGP. In particular, we talk about this network prefix hijacking attack to see if you want to hijack one network prefix, what do you need to do? All you need to do is to announce a more specific route so you can hijack that domain. We look at some of the case study, the BGP attack that happens in the real world. We look at their technical details, how exactly and those attacks work. We talk about some of the defense mechanisms, how we can protect the BGP. We did not dive too much into the details. I don't have a hands-on lab for this module yet because I'm still developing an internet simulator where you can set up the BGP speaker, where you can set up your autonomous system, and so you can really configure a BGP speaker and see how this works, and you can launch the attack by announcing this fake BGP update message. But it's going to take probably a year before I can finish that simulator. Hopefully, the simulator can become valuable, and I will develop a lab based on the simulator, so you will gain some of hands-on experience. But before that, I encourage you to look at some of the tools and the utility that I covered in the lecture, so you can look at how the BGP traffic looks like. You can look using some of the looking glass, interact with some of the real BGP speaker, and look at the traffic, look at the propagation of the AS path. That will give you a lot of hands-on experience. and some of the practical knowledge. And that will enhance your understanding of how BGP works.